Hi everyone. So today we're actually going to be talking about the cloaking, like the kind of invisibility cloaking you see in Harry Potter movies. So normally when we see objects, it's because light travels in straight lines and it bounces off objects and into our eyes, and therefore we are able to see it. So cloaking actually messes with this light in such a way that it distorts light waves according to its shape and color, and in such a way that it's invisible to the frequency range. This means that it does not give off a shadow, it should not reflect back, it does not scatter, and it bends around the object itself. It is also not detected in the background and is unchanged, and this quality will be really important for later. So applications of cloaking include communication, sensing systems, as well as security detection. As mentioned earlier, not being able to be detected is actually a very important quality. This means that it should not affect the surrounding electromagnetic waves outside, whether it's the object disturbing the electromagnetic waves or the waves disturbing it. The light inside the cloaking shower should also not escape. This also means that when being cloaked, the electromagnetic wave should arrive at the same point past the cloaking object as if it was passing through space, as you can see in the diagram. So this means that it will have to travel faster than the speed of light. In cloaking, usually we make use of metamaterials, and these materials are synthetic composite materials with structures that exhibit properties not usually found in naturally occurring materials. These materials also usually have a negative refractive index, at least the metamaterials we use, such that it can affect magnetic components and increase the range of interactions that are possible, such as no diffraction. Isn't that cool? And this is usually possible with controlling the effective permeability and the effective permittivity of the object. Usually both these qualities are less than zero. So in this part, we're going to discuss two main methods of cloaking. One is decreasing the scattering, and this is by coating the material with dielectric materials. Usually dielectric or conducting metamaterials that lowers the permittivity to be lower than the background. Then cloaking in the range of interest is possible. The wave scattered from the cloak also helps to cancel out the wave from object to be cloaked. This lowers the residual scattering and basically makes it invisible. Reducing the scattering cross-section to be zero also helps to cancel out radiation from the induced dipole moments, independent of position directory geometry, Fern, and the polarization of illuminating source. As seen from above, the shell and the object. The object has a dipole and the shell counters that dipole. The advantage of using such a method is that it is non-resonant and it's less sensitive to variations in shape geometry and the frequency of operation of cloaked object. The next method would be transformation from point to sphere. It is a coordinate transform, which is basically a distortion of ray paths, which is like the mirage effect, which is similar to that of ray refraction. It also makes use of temperature gradient, which is affected by air density, which varies with distance. This bends optical ray. This forces impinging light to travel along a specific direction, which distort ray paths to fill a given region of space by suitably designing a material. This method is actually superior to the first method because it can be applied to any size of the region to be cloaked without restrictions on its total electrical size and on its geometry. So that will be all for the video on cloaking. Thank you for your kind attention.